Hello, welcome to my talk. My name is Amir Carmel. I'm a postdoc student currently at Pennsylvania State University. Before that, I was a postdoc student at Weizmann. This is a joint work with Zhenju Zhao, Xiaofeng Jiang from Peking University, and Robert Krausgamer from Weizmann Institute. Today, I'll be talking about corsets for the one-center problem in L1 matrix. So let's start from the notion of corsets. A corset is a small subset that approximate the behavior of a full dataset, of the full datasets. So consider the set of points P in the figure to the right, and we want to compute a function f over P. This will give us this straight line. A corset then is a small subset of P with much fewer points. That if we compute f over this subset, we get approximately the same result. This is the key idea behind the corsets. Instead of solving the problem on a massive dataset P with n points in d dimensions, instead we solve the problem on a subset of it, hopefully with much fewer points. This can be done with significantly less computational resources if Q is small, and we get a very good approximation to the optimum value of P. Coresets also provides efficient storage and allows efficient communications, so it makes it very useful for streaming and dynamic settings. And why study the L1 metric? The L1 will provide us a unified approach to other metric spaces like Hamming and Tau and Jacquard. Those metric spaces can be embedded into L1, and so we will get that results for corsets in L1 can carry over to these metric spaces as well. Also, the corsets are a very geometrical problem, and so by studying corset in L1, we get insight into the geometric structure of these metric spaces. So we're not just studying corset for L1, we're actually interested in a broader range of metric spaces that share common properties. The one-center problem is also known the minimum enclosing ball problem. We start with the input set P of points in an ambient metric space, and our goal is to find the center in this metric space that minimizes the cost. And the cost is the maximum distance from this point C to any point in the input set P. And the optimum value is the radius of the minimum enclosing ball. And this is the cost of the minimum over all the points in the metric space. And we have that if Q is a subset of P, then the optimum value for Q is less than the optimal value of P, because this is the radius of the minimum enclosing ball, and every minimum enclosing ball for P is also a minimum enclosing ball for Q. And in the figures below, we see example for how balls look like in the L1 matrix. So they have this diamond shape. And in high dimension, this is known as the cross polytope. Corsets are well studied in the Euclidean metrics, but in our work, we will focus on the L1 metric. And the key difference between L1 and L2 is that in L2, the optimal solution is always unique. And in L1, this is not the case. Not necessarily the case. In this example below, we see a set of points P that have two optimal centers, C1 and C2. We can see they have enclosing balls with the same radius that enclose the set P. So a set in P in general can have many optimal solutions. Now I'll talk about the definitions of corsets. There are several definitions. The strong definition, strong corsets, is such that it gives a good approximation for every point in the metric space. So for every point C in X, we have that the cost of C, if we compute the cost only on Q, it's 1 plus epsilon to the cost on P. So in the example to the right, we see in the Euclidean plane, the ball in L2, and we see a strong corset. The blue points are the strong corsets. If we need many points because if we consider every antipolar point of a point in the original set P, there need to be some representative in the corset because we need to estimate the cost for every point in the metric space. Weak corset is different. Here we want to preserve the cost just for the optimal solution of Q. So we take Q and for every C hat is an optimal solution for Q. The cost of C hat on Q is at most 1 plus epsilon, the cost of C hat on P. And this is like we said in the first slide, right? Instead of solving the problem on P, we solve the problem on Q, and we are guaranteed that every optimal solution that we found in this process is also a good solution for the original set that we want to solve. And in this example to the right, we see that we need just 3 points. Using those 3 points, we managed to find a center that's enclosed is most of the that is a good approximation. The radius is a good approximation to all the points in P. Even a weaker notion than that is a value-preserving coset. In the value-preserving coset, we don't care about the center, but we care about preserving the radius. So we have that the coset is such that if the optimum value of Q is at most 1 plus epsilon, that's of the optimal value of P. So we have that in this example, we can just take 2 points, and maybe the center is not optimal, but the radius to enclose these 2 points is optimal. It's very close to the radius that is needed for the set P. So these are the definitions of corsets. Usually strong corsets are easier to prove than weak corsets. So usually in some application, it's easier to just prove the existence of strong corsets. But what is known in the Euclidean metric space, we know that strong corset actually requires a lot of points. So we have exponential dependency in the dimension, whereas weak corsets is dimension independent. So it's a very good result for weak corset. We can get something that is independent of the dimension. The value preserving corsets is slightly less than the weak corsets, can be half of almost half of the number of points required for weak corsets. But what about L1? So this is what we show in the paper. We show that strong zero corsets exist of size 2 to the power of D. And however, weak corsets, every weak corsets might require size exponential in the dimension. So we have a bad result and good result. So for the strong corsets, we have a good result that we need exponential, but we are independent of epsilon. And we have a zero corset, so we can estimate precisely the cost for every point in the metric space. But for weak corsets, we have a bad result because we need, in the worst case, exponential number of points in the dimension. So it requires the corset to be very large. So we would want to identify cases where we can find smaller size corsets. So even polynomial or hopefully dimension independent corsets. And we consider a natural case, which is the case where P has a unique optimal solution. So in L1, this is not always the case, but we know that this is what happens if in L1 we also have a unique optimal solution. Also, a unique optimal solution can be enforced by adding at most 2 points. So for this case, where the optimal solution is unique, which is just like in the L2 case, we have that unique optimal solutions. There is a weak corsets. It's also weak zero corsets, and the size of it is 2 times D. So it's an exponential improvement over the general case. But even if we want to have some dependency in epsilon, every weak corset must have size that is omega of log D points. So there is still a dependency in the dimension, which we can't get rid of. So next we study value preserving corsets. And we managed to show that how to get rid of the dimension dependency, and we actually get a dimension free bound for value preserving corsets. And yeah, that's our results. And now I'll talk about our techniques. Okay, well, for the strong corsets, we show that by selecting points that maximizes the dot products for every sign vector, if we take these sets of points, this is a strong zero corset. And the analysis is tailored to the L1 ball, because in the L1 ball, we have that each face of the L1 ball is associated with one of the 2D sign vectors. So we managed to analyze it by selecting just those points, we get a strong zero corsets. For the lower bound, we have to construct a hard instance. We have to construct an instance that has many optimal solutions, and that each point in the instance restricts somehow the sets of optimal solution. So even if we take a subset of the points in P, we get an optimal solution for this subset that is far away from some point in the original input set. So this is a well-structured case. For the unique center case, we use Steinitz theorem from convex geometry, which is not so popular, but we managed to show using this theorem a nice lemma that says that if you have a sphere then every cover of the sphere with open hemispheres has a subcover of size 2 times d. And using this lemma, we managed to show that if we take an instance P that has a unique center, then it means that you can't shift C in any one of the directions. If you consider just like a small sphere around it, you can't move the point to any direction because you deviate from one point in P. We show that we can associate each set points is something like restrict some open hemisphere in on the sphere. And using this lemma, we managed to show that we can get a coset of size 2 times d. For the value preserving constant, we have something of we have a random sampling technique, which is quite well for one center problem or minimization problems in general, because in minimization problem, usually we need to consider every point in P because every point in P can affect the optimal value. So usually random sampling is not so common in this kind of problems. We managed to obtain, we show that our innovation is that the sampling probabilities can be obtained from the dual linear program. And when we sample points from this distribution, we get a sample that is almost a feasible solution. So it's not without any additional constraint, this is not a solution, but it is an almost feasible solution. And now we have a lot of sets of equations that are imposed by the dual program that we need to satisfy. So because this is the almost feasible solution, we must modify it. We apply careful modification that on the one hand, we don't change the sets of points by much, and so the optimal value is not changed by much. But on the other hand, we manage to show how we can satisfy a large set of equations. And once we balance all these dual constraints, we obtain with a feasible solution. So it provides a bound on the objective value. And this bound, we show that it doesn't deviate by much. It's just a 1 plus epsilon approximation. So we actually show how we can just sample number of points independent of the dimension, and then obtain a good solution. Okay, we still have open problems left. For the unique center case, there is an exponential gap between the lower bound and the upper bound. So there is a significant room for improvement. For the value preserving corsets, the bound is inherent to the technique. So maybe using a different technique, we can get a much smaller bound. And also we ask the question, what about k greater than 1? What if we have several the k-center problem, and we want to have corsets that support the k-center problem? That will be all. Thank you for your attention. And if you have any questions, feel free to send me an email. Thanks.